Aqui na página.
So the second lecture of this afternoon session is about CP violation by Professor Castello Branco, please.
Okay, I will start by thanking the organizers, in particular Professor Mario Novello and Professor Vidiaga, for the kind invitation to come back to Brazil and to Rio de Janeiro. It's a great pleasure. Muito obrigado. Okay, so I'll be talking about CP violation, and I think it's appropriate because, you know, cosmology has to do with galaxies and stars and so on, and without CP violation, it seems that we cannot have matter, okay, in the universe. So, and we need matter in order to have galaxies and things like that. Okay, so let me. So I'll start by giving a brief review of the flavor structure of the standard model. Why? Because within the standard model, the question of CP violation and flavor are intimately connected. Okay, as you see, it doesn't mean that in general it has to be that way. In different contexts, okay? CP violation is a separate issue, but within the standard model. So what is the standard model? The standard model, as you know, is a gauge theory based on this group, you know, on the SU3 cross SU2 cross U1, which is an incredible successful theory. I would say, maybe you will disagree, that it's after general relativity and quantum mechanics, the greatest achievement of fundamental physics is the standard model. It's an incredible, also not only merit of the builders of the standard model, but also luck. You know, luck also plays a role in physics. Now, so the rules, this is a school, so I will start from the beginning. It's just choosing the group, you know, SU3 color, SU2L, cross U1. This group was actually suggested by Glaser in his thesis in 1961. But until contact with reality, it took a long time, you know. So the rules of constructing a gauge theory are very clear. You have to, I mean, associate gauge fields to each generator of the various groups involved. Here, these are what I here. This for gluons for QCD and the W's for SU2 and so on. So you, from these basic fields, concentrating now on the weak sector, because that's where CP violation arises, concentrate on these fields, you know that you will see that later on we'll construct the chart currents. And oh, I'm sorry. No, and so that's why we had the idea of putting the left-handed quarks in a. I'm sorry, I keep pressing the wrong. Left-handed quarks in a doublet, while the right-handed quarks on a singlet. Okay, the left-handed leptons the same way, you know, and no right-handed neutrinos. Now, I will anticipate a little bit my comments about neutrinos. It's amazing. one of the things of the standard model is simplicity. Now, I will claim that, first of all, standard model has been ruled out by neutrino oscillations, because in the standard model, neutrinos are strictly massless. Okay, they are massless at 3 level and more. They are massless at all orders of perturbation theory. They cannot also receive contribution from non-perturbative, because B minus L protects them from anything, so they are exactly massless. And the builders of the standard model, particularly Weinberg, Glashow, and Salam, were very proud of that, because it's non-trivial to have a model where neutrinos are massless to all orders. I mean, at that time, at least, we're very proud that not only in 0 level it was massless, but also in any higher order. You cannot have a neutrino, a theory with a neutrino of order alpha multiplied by neutrino by the electron mass. Okay, that will be completely ruled out. So they were very proud that neutrinos are strictly massless. But if they would obey to their own rules, which is simplicity and renormalizability, what the rules at the time was to write the most general Lagrangian consistent with renormalizability and gauge invariance. Then they should not put in their pocket nu r. They should put nu r there and not be afraid of having a Dirac mass. They had, of course, a Dirac mass. That would be only that would be very bad. But then the fact that you could write a right-handed Majorana mass, that immediately leads to a seesaw mechanism. Of course, it's easy to tell this story now that we neutrinos have a mass, but this was not the motivation for people who built the seesaw. You know, seesaw, for example, I asked Pierre Ramon once he was visiting Lisbon, asking, how did you come up with the seesaw? You know, he said, well, we didn't have a choice, because in SO10, you could not do what Weinberg and Salam did, to put in their pocket the nu r. Nu r has to be put, and therefore they have to find the justification, and it was discovered. But even without grand unification, once you put nu r there, you have the seesaw. Okay, that's what my point is. Of course, we don't know what the scale is. You know, this is one other thing. Oh, for the mass of the nu r. You know, now the scalar fields, it is the same thing. This minimal model. At that time, in the beginning of gauge theories, the standard model, people didn't believe that the Higgs should be taken very seriously. I mean, maybe the mechanism, yes, but not exactly one doublet exactly in the standard model. People thought it was just an indication, but the things will be different. Unfortunately, the nature, it seems to follow the standard model, apart from the question of neutrinos, okay? Now, so this is the usual rule for the covariant derivative, and you have just to choose a representation. Immediately, gauge theories tell you how to build the Lagrangian. Now, of course, to specify the generators, you have to choose the group representation. These are the choices for the SU3. You have Gell-Mann matrices. Here you have the tau matrices and so on, and that's how you have everything well-defined gauge. It's a beautiful theory, no question, but it has nothing to do with reality, because gauge fields were massless. You know, that's why even when the Gell-Mann, Young and Mills suggested the non-abelian gauge theories, things took a long time to develop, because we could not give mass to we could, but then the theory would not be renormalizable. Renormalizability at the time was very important, okay? People really, that was the motivation for gauge theories in a way. So, but fortunately, it was proved, that was a real revolution in 1971 by Geweltmann, his student Etoft, that gauge theories, even with spontaneous symmetry breaking, you know, you could generate mass to the W and Z, and therefore have the hope of being in agreement to experiment, and still renormalizability will be kept. That was an incredible thing. If you look at the papers appearing before 1971 on gauge theories, after 1967 paper by Weinberg, still there were no one who was working on gauge theories, you know, at that time. But after 1971, it was an explosion. And and the standard model has one characteristic that is important. If you put the Higgs potential, the most general one, I'm sorry, I keep pressing, in the most general one, you you have to put lambda larger than 0 so that it's bounded below, but you have two choices, either mu square larger than 0 and then you have a trivial minimum, or mu square less than 0 and you have a minimum at a non-trivial value. And this one that will break gauge invariance, but will cap the invariance of electromagnetism. So this is the usual things that we have seen many times, I'm sure. This is the minimum that is interesting, this one. But the electric charge is always conserved. You know, this is non-trivial, again, because it's in extensions of the standard model, including supersymmetry, electric charge is not necessarily conserved. Okay, he is automatically conserved. So you can see that, for example, the charge operator acting on this vacuum, it does not change it. It annihilates the vacuum, and therefore the gauge transformation is invariant. The vacuum is invariant under this gauge transformation corresponding to electromagnetism. So let me emphasize some important points. Electric charge is automatically conserved. This is no longer true in extension of the SM where 2x doublet, for example, which implies that includes the case of supersymmetric extension of the SM. As you know, in supersymmetry you need 2x doublet. In the general 2x doublet model, for example, without loss of generality, one has this. This you can do by making a gauge transformation, but you have here y that is not automatic. You cannot put equal to 0. You have to choose a range of the parameters where y is equal to 0. In that region, charge is conserved. Yes? Which symmetry? If y is different from 0, yes. Charge will not be conserved, okay? But I always give the example of T.D. Lee because he had already a Nobel Prize, and he wrote a paper in order to put, this has to do with CP violation, in order to put the breaking of CP at the same level as the breaking of gauge symmetry. In other words, should be spontaneously broken. At that time, there were only 2 generations, okay? Even incomplete, because charm, I think at that time, had not been discovered, 1973. So he built this model with 2x doublet, and he was very careful. He did a very careful calculation of Higgs potential, which is quite tedious to prove alone, because the paper has only himself. You know, he didn't. The fact that he was a famous physicist, he didn't, you know, prevent him from doing this, because this is very important. Imagine that T.D. Lee would write a paper where charge would be violated. Now, he's a very tough guy, and he would not be happy to see someone pointing that out to him. But he proved not only that there is a region where y is equal to 0, charge is conserved, but also a region where theta is different from 0 or pi, and in that for those values, CP is violated by the vacuum. In this lecture, I'll be talking about 2 types of CP violation. One is caused by complex Yukawa couplings, and one that is Yukawa couplings are real, but the vacuum violates CP. These are 2 different types of two ways of thinking. For those who are asking, but what about Kobayashi Maskawa? Doesn't that prove that Yukawa couplings are complex? No, I will show you. It's very easy to even to say by words now that is not true, because you can have, if you have 2x doublets, the masses are generated from the 2 Higgses, and Yukawa couplings are real but arbitrary, if you want spontaneous. But because you have this theta, the 2 sums with arbitrary or real couplings, you can generate mass matrix the way you want, and you can generate CKM from this single phase. Okay, it's a very interesting thing. Now, the model as T.D. Lee suggested is ruled out by experiment, but it is possible to have extra symmetries that save the model. The model is ruled out because of the flavor change in neutral current mediated by Higgs. Okay, so that is the reason why the model, as it was ruled out, but you can have symmetries that save the model. Okay, I will not talk much about that. It's something very recent. So the charges of in the standard model are completely arbitrary. You have to choose the hypercharge in such a way that you have the correct charges. Okay, so you choose. Yes, absolutely, absolutely.
So there are 2 solutions affecting the anomaly cancellation. One which is somehow pointing to this, and then there is another one which is unfeasible.
Yeah, that's true. Another way, as you know, is SU5, and SU5 is beautiful. Even the standard model, yes.
Anomalies, if you also add the gravitational sorry, T mu YY. YY, Y cube, and then the other ones restrict the charges to.
That's a good point. Yes. Very good. Yes, but I want to. It does not come automatic unless if you take into account these constraints. Yes. So now we also do not explain why the charge of this certainly has cosmological implications, right? The fact that the proton has a charge equal to the electron apart from a minus sign, so that you have neutral atoms. But you can find a solution to this fundamental question in the framework of grand unification. By the way, grand unification again helped in people like Glashow believing that neutrinos are strictly massless. Because grand unification was suggested in 1974 by Glashow and Georgi, and I heard the story that actually they had discovered SO10, but then SO10 they didn't want because right-handed neutrinos are there, therefore they discovered immediate SU5, which is a beautiful theory. And in SU5, by chance, B minus L, I mean by chance because B minus L is an accidental symmetry of SU5, and because of B minus L, then neutrinos were strictly massless to all orders in perturbation, okay? And again, no, they don't have, SU5 doesn't have anomalies. This was mentioned now, yes. Yeah, I should have mentioned that. That's a very interesting point, yes. Okay, so convenient parameterization is done in this way, and you can have a spontaneous gauge symmetry breaking, and if you expand around the vacuum, you define these fields H0 and G0, the G plus minus and G0 through the Higgs mechanism. They would be Goldstone bosons because the theory, as you know, by the Goldstone theorem, a theory with a continuous symmetry that is spontaneously broken leads to Goldstone bosons. But in the case of Higgs mechanism, these are absorbed as longitudinal components of the fields that acquire a mass, and the mass is predicted, okay? It's an incredible thing that the gauge theories were able to predict masses of the order of 100 JeV. You know, there is a book by someone who is famous, now people don't talk much about him, but V minus A theory was invented by Marshak and Sudarshan, and together with separated by Gell-Mann and Feynman. But there was a book of gauge theories, of weak interactions by Marshak, which appeared exactly right before the gauge theories, before 71. I don't remember the exact date. But in that book, it talks about intermediate vector boson theories. And this suggests for the mass of this intermediate vector boson that would mediate gauge interactions, 2 JeVs, you know, because this was what people could think of for an elementary particle of 2 JeVs, 3 JeVs, not 100 JeV. You know? Only with gauge theories, this completely abnormal idea of elementary particles with 100 JeV appeared. And fortunately, not only they were, it was not too high mass, and therefore they could be discovered. You know, okay. There was also a prediction, a very important prediction, that there should be a neutral gauge boson, you know, that this was, and its mass was also predicted, this beautiful relationship, you know. Again, it was luck that standard model not was a great breakthrough, but had a series of simple predictions that could be checked in the near future. In this framework, of course, we recover the photon. That's a combination of these fields associated with hypercharge and T3. So you have these relationships that are well known, the photon and the Z with respect to these ones. Okay, and there is a letter theta W. Theta means for weak, not Weinberg angle, because the angle was actually introduced by Glashow, you know, so it would be unfair. So it's the weak angle, you know, theta W is for the weak angle. So Fermi masses. Now, I mentioned that gauge bosons acquired mass through spontaneous symmetry breaking. But the Fermi masses, which are crucial for CP violation, are going to be also acquiring masses in the standard model through gauge symmetry breaking. For example, they cannot have masses at 3 level because this mass term, for example, this is a doublet, this is a singlet, therefore this is not gauge invariant. And one of the dogmas is that you cannot write anything that is not gauge invariant at the Lagrangian level. Therefore, this you need to. The fortunate thing, fortunate or unfortunate, we don't know, is that the standard model, the masses of the standard model could be generated again from the Higgs, you know, the same Higgs. So let me repeat, all Fermion masses are protected by gauge symmetry. This is a very important feature of the standard model. Consider, for example, standard model is grand unified through a gauge symmetry that is larger than GCM, where G could be SU5, SU10, could be E6, whatever you want. Since Fermion masses are not invariant under this group, they do not acquire a mass, it will be very heavy, when the breaking of this large group into GCM. See, because they are not invariant, these masses, okay? So they are protected from this very large mass. So they only acquire mass once SU2 cross U1 is broken, okay? So this will be a disaster because, you see, for example, in SU5, the 24 gauge bosons of SU5, 12 of them would acquire mass in this breaking, and to be of this order. And if the fermions would be invariant, you know, under SU3 cross SU2 cross U1, they would acquire mass in this stage of breaking, and this mass will be enormous. Okay. Now we know that they need the Higgs, the vacuum potential value of the Higgs. So, taken from this point of view, we do not the most natural mass for fermions is actually the top mass. Top mass is the only one that is of the same order of magnitude as V. You know, so in a certain sense, the only mass that we understand is more or less the top mass. We don't understand why there are so light fermions. Okay, because there is a huge hierarchy there again. So as I mentioned, the masses are going to be generated again from the Higgs, you know, the same way, and they will be proportional to these Yukawa couplings. Now, the Yukawa couplings, this is a very important point. Gauge invariance does not constrain the flavor structure of Yukawa couplings. You know, they are completely arbitrary. So we do not understand the replication of families, and also we don't understand the structure of the masses of the fermions. We don't know that. You know, it's completely. In a way, it is good that the gauge invariance does not restrict them, because it could restrict and rule out the standard model. But it is bad because we don't know how to calculate, okay? There are many, many people who have tried to have extra symmetries, extra family symmetries, and so on. I like to mention here something that is attributed to Feynman. I don't know if it's true or not. It's a poem. He says, you want to be famous. You want to be a king. You want more than a Nobel Prize. Then solve the mass problem. Now that problem is still with us. You know, we don't know how to solve the mass problem, how to understand why the electron has a mass completely different from the muon and so on. Since the time of that appeared, the second generation, in particular the muon, that we have this problem with us and we don't know how to solve. Okay, I believe that this, maybe you would not agree, but I believe that it is possible through standard particle physics to solve this problem. But we need to have ingenuity. I'll give some suggestions why, in my opinion, this could be difficult, why it is so difficult from bottom-up approach, okay? But this freedom, you know, to have the Yukawa couplings, you know, not constrained, it allows us to fix the couplings in such a way that you get the correct masses. Now, yes? Is there anything in the standard model that constrains? No. I mean, unless other constraints, but I mean, from the standard model itself, yes, the number of families is not defined. But we know experimentally now, standard families, we cannot have more than 3, okay? Yes. Also asymptotic freedom, yes. Yes, but this is sort of phenomenology, you know, yes. But it's very important, yes, that is the... But as far as the possibility of having, for example, a 4th family, that is being ruled out. But there is something much more interesting, which is to have a vector-like particle. In other words, a particle that left-handed and right-handed transform in the same way. Okay, that is a very interesting possibility. It's still not ruled out. Okay, so now you see these masses coming back to the masses of the quarks. You see, if you think of this, this is a totally arbitrary complex matrix. Now it's easy to do the counting. Okay, 3 by 3 matrix complex, so it's 18 parameters. You know, and up 18, in the down 18. So you have 36 parameters. You may ask, where are they? Why are these parameters? No, because they are not physical in the sense that you can make weak basis transformations. A weak basis transformation is a transformation of fermion fields in such a way that the gauge currents maintain diagonal in flavor. You can do transformations that change M up, M down and M up, change completely, and the physics is the same. You can, for example, go to a basis where M up is diagonal, and all the physics, all the masses of the downs and the mixings will be dictated by this MD family. Furthermore, you can choose these that need not be Hermitian, but you can make a weak basis transformation that they are Hermitian. Therefore, all the physics will be contained. You can do the counting. This will have 3 parameters, real, the masses, and this will be another 7 parameters, you know. And there are 7 plus 3 is 10. 10 is the number of parameters that you have in the quark masses. 3 plus 3 is 6, and then the 4 parameters in the Kobayashi-Maskawa matrix. Okay, so you can have a basis where you can read from the experiment, you know, the quark mass matrices. But in general, you see already immediately you see a difficulty in some kind of intuitive bottom-up approach. You may say, well, why don't we look at the quark mass and try to invent a symmetry? But in what basis? See, what basis? You may say, well, I like this one, but why should it be the one that where this is diagonal? It's not easy to get from experiment to get into the theory. Okay. Similarly for leptons, you have the same thing, but you have charged for the charged leptons, you know, something like that. I already said that in the SM Yukawa couplings are the only couplings which can be complex. What about neutrino masses? So I'm repeating myself, but I think it's worthwhile emphasizing. No Dirac mass because nu r, as Giunti already explained very clearly, nu r is not introduced. No Majorana mass at the level because this is not a gauge invariant. You would need the triplets. And no Majorana mass in higher orders due to the exact B minus L conservation. Okay. So once you have these mass matrices, you want to have to go to diagonalize the matrices, and this can be done for an arbitrary complex matrix by biunitary transformations of this type, you know, and it's very well known. And once you do that, then the initial gauge currents that are written in this way, you know, for example, here, they will be transformed. This one will be rotated with some UU matrix, this one with UD, and therefore you appear here with a VCKM, Kabibu, Kobayashi, Maskawa, UU, L, UDL. Let me now make a statement here in praising Kabibu, okay? You may say, well, this all looks so trivial, you know, why we talk about Kabibu mixing? Kabibu, in my time when I was a graduate student, people were talking about Kabibu universality, which was a great breakthrough before quarks were invented, you know, we didn't have gauge theories. It was a beautiful idea to make, for example, strange particle decays, neutron decay, muon decay, all belonging to the same thing. Why should people used to talk about, you know, universality of weak interaction? Because they could be in principle completely different theories. And Kabibu did that, okay? So that is something that cannot be compared to difficulty, which is none, to understand Kabibu mixing, flavor mixing in the context of gauge theories, because gauge theory have built-in universality, you know. The gauge coupling, I mean, it's trivial what I'm saying, but it's very important. The gauge coupling associated to SU2 has the same value for leptons, for quarks, you know. It's a very important. This is non-trivial if you don't have gauge theories, okay? So you may ask, is the matrix UL that diagonalizes the charged leptons physically meaningful in the context of standard model? The answer is no. since neutrinos are massless in standard model, one can always redefine neutrino fields. You know, this can be, you have initially this because of the organization of charged leptons, but this you can always redefine neutrinos because they are massless, that these are the ones that you want. Therefore, if you do that, then there is no mixing, okay? This is very important, recuperating the idea that the neutrinos, that in the leptonic sector, in the standard model, there is no mixing, therefore no oscillations of neutrinos. I will go quick now. The electromagnetic current, again, is the same happens, you know, you do the same, and becomes flavor diagonal. It is flavor diagonal in the beginning, and it is flavor diagonal in the end, because all these matrices cancel. What is non-trivial, and was a prediction of the standard model, is that in the neutral currents, you know, the neutral current can be written in this way. This is T3. You know, this is T3, essentially, this with minus here. It's T3, the generator of T3, and then with electromagnetic. So anything that all that you have to worry is about this, what happens here. And if you have all the quarks of left-handed quarks in the same value of T3, then you have to sum of all of them. This matrix will become 1. You know, this is generalized GIM. You know, GIM is the mechanism that Glashow, Iliopoulos, and Mayani conceived to avoid neutral currents. Because the idea of neutral currents was very old, but there was a very strong experimental prejudice and justified prejudice against neutral currents, because if they were forbidden, the ones that change flavor, okay? And therefore, you have to have a mechanism to save that, and this was created by the GIM mechanism, the cancellation of flavor change in neutral currents. So this, since following the tradition that Brandenburg introduced, giving homework, so exercises, suppose the charm did not exist, so that one would have this, you know, something like that, showed that in this model flavor change neutral currents automatically arise. It's not a question that you could put fine-tuned to 0. No, they automatically appear, and with the strength very well defined. Therefore, it would be a tragedy. That's why people didn't want neutral currents, okay? I heard that there are many experimental physicists that in their thesis, they had neutral current events that were somehow eliminated before the gauge theories, you know, because this was for sure background could not be neutral currents, okay? Because they didn't have a good theory to tell them, look for neutral currents, they exist, okay? So the theory and the experiment go together. It's very important, you know, in our field to have theory and experiment to go together, okay? So this is what I'm explaining here. Prior to the rise of non-arisal gauge theories, physicists considered the possibility that weak neutral currents could exist. However, there was a strong prejudice against neutral currents due to stringent limits on strength of flavor change in neutral currents, okay? I'm sorry? Isso experimental. Sim, vou já dar you are going to understand immediately. This is the beautiful argument is K0L goes to pi plus electron and antineutrino at a strength normal of weak interactions, okay? Now, this diagram doesn't exist in the standard model, that if they would exist, you know, this neutral current violent flavor would exist, this would have the same essential lifetime as this one. And as you know, in the particle data group, this is much, much, much less weaker than this one, okay? Because this coupling does not exist. This happens in the standard model, but in higher orders, okay? This is another thing that standard model not only tells you what is at 3 level, but enables you to calculate things at higher loops. And everything, unfortunately or fortunately, goes well, is in agreement with the standard model, with some very rare exceptions. Neutral currents interaction violate parity. For example, you have you know, Z mu coupling with gamma mu, and also Z mu coupling with gamma mu. The fact that they both exist with the same particle, it leads to to parity violation. Those who are old enough to remember the issue of, at one point, two experiments of very good groups, Oxford and Seattle, Washington, Seattle, they were saying that there were no parity violation in atomic physics. That really shook up, you know, many, I'm not going to mention because it's not fair. Very famous physicists were considering, including the builders of the Standard Model, you know, they were very shaken because this would be not in agreement with the Standard Model. They were considering other possibilities. There was actually a theory that was very, very nice with the left-right symmetric theories where, again, you would have another Z. You know, if you have two Z's, then parity is not violated. All you have to do is to assign parity difference for this one and this one. But this is the same particle in the Standard Model. Therefore, you cannot do that. Therefore, parity violation you have in atomic physics. They were discovered after some misleading experimental data, as I mentioned. Okay, these are the diagrams that lead to the same phenomenon that is forbidden at 3 level, DS coupling, but in a box diagram you have K0, K0 bar mixing, BD, BD bar mixing. And this even led diagram like this without the top. At the time we didn't discover, we had not the top. Led the correct estimate of the charm quark mass by Ben Lee and Mary Kay Gaillard. Okay, that was an incredible thing. It was a few jab, you know, the prediction. And soon after, the charm was discovered. Anyway, so another exercise. And this is very, very interesting because it could be true. Physics beyond the Standard Model. Consider a simple extension of the Standard Model. I'm sorry. Consider a simple extension of the Standard Model which consists of the addition of an isosinglet quark to the Standard Model. See, this is not a 4th generation. This is just a singlet quark. Okay, that is nothing wrong in that. You know, it's something in a way similar to the right-handed neutrino. Right-handed neutrino can have a bare mass, right? Because it's gauge invariant. The same way, a bare mass to this guy, you know, d bar L dr is allowed by gauge invariance because it's a singlet. But it turns out, if you do it's worthwhile doing this exercise. Write down the most general quark mass terms which are obtained in the framework of this model. These are the general rules of gauge theories. Derive the structure of charged currents. Derive the structure of neutral currents, showing that there are flavor change in neutral currents in this model. So you may think that I'm doing something crazy. No, because in this model, there are flavor change in neutral currents, but they are naturally suppressed by small mass over large mass. Similar to what you have actually in the neutrino sector. In the neutrino sector, there are also flavor change in neutral currents at 3 level. No one talks about that because this is suppressed by seesaw scale, you know. But strictly speaking, this phenomenon already appears in a very well-established mechanism that people accept. The simplest mechanism to generate masses for neutrinos is just seesaw, you know, which can appear even with the Standard Model added with nu R, which, you know, as I mentioned, it is simpler even than the Standard Model. Okay, it's this new SM, and then show that non-vanishing flavor change neutral currents are naturally suppressed in this model. This is a good exercise. So neutral currents, as I said, have played a crucial role in the construction of Standard Model in its experimental tests. The discovery of neutral currents was the first great success of the Standard Model, in my opinion. I think people share this opinion. The control of flavor change neutral currents is a beautiful way through GIM and generalization of GIM. EPS prize was given to Gargamel collaboration in 2009. It took a long time, but why not the Nobel Prize? That's a good question. You know, my experimental colleagues tell me that it's because Gargamel, the leader of Gargamel, somehow he passed away quite young. So in order to win the Nobel Prize, not only you have to be very good and very lucky, but also not die too soon. You know, he died like it happened. Yeah, of course, many other things, of course. But Braut, and one example that is very sad is Braut. You know, Braut Anglais, you know, he died, Braut. He was a very good guy.
Cabibbo died also.
Oh, Cabibbo was, yeah. But that was very unfair. That. Yes, yes. No, but that was very unfair, in my opinion, okay? He should, yeah, Cabibbo should have received the prize, you know. Anyway, so, and I mentioned already that loop level flavor change neutral currents are generated, and they play even today a crucial role in testing Standard Model and putting bounds on new physics. K0, K0 bar, D0, all this is predicted within the Standard Model. SM contributions to this process are only at 2 level, so new physics has a chance to give significant contributions. Let me add the following. I will show you in the next lecture some beautiful plots where, as a result of great work done by experimentalists, you can see how well the Standard Model does. So you may say, well, then it means that new physics is very much suppressed, you know, very little only. No, it's not true. You can have, for example, contributions to these processes like K0, K0 bar, D0, D0 bar, etc., at, say, 10% level, and I'm being even conservative, probably even 20% level, amplitude level, and still in agreement with the experiment, okay? This is, there is space, so people who work, I know that some people here work in LHCb, you should not think that this is hopeless to discover new physics in, with a rare process and so on. It's still possible that you have. And this kind of model that I mentioned with the vector-like quark is one example where you can have new contributions to all these mixes that affect completely the so-called unitarity triangle. Now, come finally CP evaluation. How does CP evaluation appear? Now, we know that CP evaluation is a fundamental phenomenon. You know, it is a crucial ingredient to generate binary symmetry of the universe. It plays a crucial role in the search for new physics beyond SM because it's closely connected to flavor. Okay, and to test CP evaluation is also to test flavor. Okay, how much time do I have?
You have more than
10 minutes. Okay, very good. So, so one may ask, what is the origin of CP evaluation? In general, this question, in general, it is an open fundamental question. We don't know really what is exactly the origin of CP evaluation. We have many possibilities. In particular, we don't know the answer to this question. Is CP evaluated at the Lagrangian level or by the vacuum, like in gauge symmetry? So the violation at the Lagrangian level was suggested by Kobayashi and Maskawa, 1973. The same year appeared the model of TDD. I was a student at City College at New York City, so that's where Columbia is. And I remember very well, people were paying a lot of attention to the, in part because TDD was at Columbia, I was at New York, to this model, okay? But Kobayashi Maskawa, it's also a very interesting possibility, is just allowing for CP being at Yokawa couplings, okay? So I will mention here something that probably you don't hear, but in my opinion is the most rigorous way of saying why it appears, CP evaluation in the standard model. It is a clash between CP properties allowed by gauge interactions. You know, gauge interaction necessarily conserves CP. You know, it's something that's been proved by Grimus and Rebello. But Yukawa interactions not. But so it is the properties required by gauge interactions with those allowed by Yukawa interactions. The clash of the two. You cannot say that CP evaluation is here. CP evaluation appears because of these two at the same time. And I will explain that in two different ways in a very clear way, okay? So, important point. In the study of CP evaluation, one should allow for the most general CP transformation. Typically, LCP leaves a large freedom of choice in the definition of CP transformation. CP is violated if and only if, by the Lagrangian, you know, only if no possible choice of this CP transformation leaves the Lagrangian invariant, okay? For a review, I have this, I advise you this book that we have published in Oxford University Press. So CP evaluation can be investigated in the Fermion mass eigenstate basis or in a weak basis. You know, even before symmetry breaking, you can study if Lagrangian violates CP or not. Okay. An important point is that pure gauge Lagrangian is necessary CP invariant. Let us study CP properties of standard model after spontaneous. This is the simplest way, and this is the usual way people study. After spontaneous symmetry breaking, and after diagonalization of quark mass matrix, you have something like that. And I'm putting here that these are non-degenerate, okay? I'm assuming that they are non-degenerate, because if they are degenerate, I have to allow for a different type of CP transformation, because they are degenerate. If the up quark is degenerate with the C quark, the standard model, then there is no way of distinction up and charm. I have to allow that under CP, the up goes to charm, because they are the same part, they are not distinguishable, okay? So I put here non-degenerate as an assumption, okay? So, so I can write the most, in the mass eigenstate basis, the most general CP transformation, these are the usual ones, nothing different, but here I'm putting a certain quark charged 2/3 goes to the same quark, because I'm assuming they are not degenerate. And I'm assuming that the masses are already being generated. So this alpha is the same as here. Okay? And the same thing for the downs. Okay? So invariance under a charged current, you put this in the Lagrangian, and you see that in order to be CP invariant, this relationship has to be satisfied. Now you can see that these are free phases, so obviously any individual one can be satisfied. Okay? And if you choose a particular alpha, particular k, you can always choose these parameters in such a way that this is satisfied. So if one considers single element of BCKM, the previous condition can always be satisfied by using the freedom of choosing these phases. However, it can be readily shown that condition constrains all quartets and all rephasing invariant functions of V to be real. Therefore, there is CP violation in the standard model if and only if any of the rephasing invariant functions of VCKM is not real. Okay, that is true for the standard model, any number of generations, not only 3 by 3. Okay, you can see right away. We'll see that automatically this will be satisfied in 2 generations, but in more than 2, there will be cases where you can have CP violation. Okay, so there is a traditional C parameter counting. These are the number of parameters in a NG dimensional unitary matrix. If we do the counting, these are the total number of physics parameters, because this is NG squared minus the number of phases which can be removed by rephasing of the quark fields. So you get NG minus 1 to the square. You get 4 free parameters. Okay, these 4 free parameters can be, if you parameterize through Euler matrix and phase, it leads to 3 angles and 1 phase. Okay. So here there is a mistake. You know, it's NG again. So if you do this number of angles, so it's for 3 will be 3, but there is NG also here. I forgot. So you get, this is the number of physical phases. Subtract the number of parameters minus the number of angles. So you get this magic number. 1 minus NG. So you can see that for 1 or 2 generations there is no CP violation, but for 3 generations you can have. Another way of proving this is, for example, for 2 generations, you could do the same for 2 generations, trying to calculate a rephasing invariant. This is a rephasing invariant for the 2 generations. However, orthogonality, from here, if you multiply by VUS star VCS, here you get the moduli, and here you get the argument of this. You know, so you take imaginary part of that, and you get 0. So Q U DCS for 2 generations is necessarily real. You can form a rephasing invariant, but it is necessarily real. Okay, that's one way. There are other ways of attacking this same problem. In my opinion, much more beautiful. Okay, you could ask, well, you are already talking about mass matrix. What about the Yukawa coupling? How do I know that Yukawa coupling violates it? I will address that question. That's much more interesting and is more. Okay, so consider now another characteristic of in the standard model. Consider orthogonality of the first 2 rows. You know, just put like that. If you multiply by VUS, VCS, you get here the modulus. Then immediately you can check that you get the imaginary part. Here you get the imaginary part of this quartet. Here you get minus the same thing, but goes to the other side, equal to that. So in an analogous way, one can show that for NG equal to 3, the imaginary parts of all quartets are equal up to a sign. And there is a sign. So this is a very interesting characteristic of the standard model. You can talk about the strength of CP violation in the standard model as being the imaginary part of this quartet. And it is indeed small in the standard model, not because the phase is small, but because the angles are small. You know, you can always choose. You can choose any quartet. If you choose the quartet with position 1, 2, 1, 3, 2, 3, immediately you have a tremendous suppression just because the angles are small. But the phase could be over the 1, and that particular phase gamma, it's the angle gamma that appears in the standard model, and it is not small at all. Okay, so that's the thing. So do I have 5 minutes? Okay, so I will do the geometric interpretation of this imaginary Q. You have this here. You can construct the triangle. Under rephasing the triangle, under rephasing of quark fields, the triangle rotates. So the orientation, usually you see the unitary triangle put in this form, but it could be this is in the real axis just because I chose a phase convention in which VCB and VCD are real, but it's not necessary, okay? They have there is no meaning of orientation of the triangle. This is interesting to emphasize because here we are talking about Dirac particles. In the case of neutrinos, I will also talk about that, the so-called Majorana type triangles, the orientation is physically meaningful, okay? Here there is no meaning. Under the three-phasing triangle rotates, orientation has no physical meaning. Now another point that is worthwhile emphasizing, you can define the internal angles of this triangle in this way. Alpha is the argument of this rephasing invariant quartet, the other rephasing is alpha, beta, gamma. Now in the beginning of unitarity triangle, there were very good people, not only experimentalists, also theoreticians, good friends of mine, who are very good physicists, that used to say, well, we have to check that alpha plus beta plus gamma is equal to pi. This is a totally nonsense because alpha plus beta plus gamma is equal to pi by construction, by definition. See, if you put the argument of the product of these two quantities, you see that everything cancels. This one cancels with this one cancels with this one, and so on. You see that it's a real quantity with a -1 sign. So alpha plus beta plus gamma is equal to pi by definition. Therefore, one should talk about beta and gamma, okay? Alpha is just pi minus alpha, minus beta minus gamma, okay? This is true by definition, not a test of unitarity. I will tell you then how one can make tests of unitarity, okay? But that's a different issue, but not by measuring these angles, okay? I've not given the geometric interpretation of imaginary Q is the area of the triangle. You can see that by this picture that if you calculate the area, you get 1/2 of the imaginary part of this. So all triangles have the same area. All unitarity triangles have the same area, but they are not similar. There are some triangles that have, this shows exactly what the situation is. Wolfenstein is very clever in finding simple solutions to complicated issues. So he suggested that we should just, to get the order of magnitude, you should just put the powers of a particular, could be powers of Cabibbo, lambda, lambda cube, lambda square. If you do the various triangles, you can see that there are triangles like this one, for example, lambda, lambda, lambda to the 5. So this is not a very interesting triangle. It's a very squashed triangle. The interesting triangles are the so-called this one, VUD, VUB. This is the most, when people talk about unitarity triangle, they refer to this one. All the sides have the same order of magnitude, and they are this particular one is very appropriate to test the standard model. There is another one that is interesting, that it has signs of the same size, but these are not as well measured experimentally. VTD is not directly measured, only from BD, BD are mixing. While here everything is measured with, well, VTD also, but I mean, most of them are measured through direct measurements, okay? So this one it's useful, but it's not as much used. Now, I already mentioned this. So the strength of CP violation, you can again recapitulate what I said before. You can see right away that here you have a suppression factor of lambda to the 6 multiplied by sine of gamma. And therefore, but you could ask what would be the maximum, if you forgot about mixing angles, what would be the maximum value of this imaginary part of the quartet, okay? If you allow freedom. Then it turns out that the matrix corresponds to this one, which appears in a similar way in some models of leptonic mixing. But anyway, this is not realized in experiment because this is not true, But the maximum value will be 0.096. I will stop here, and then next time I will give you another derivation. It's worthwhile. CP violation is a very subtle issue. It's worthwhile understanding things in many different ways and see that everything fits together, okay? So I will talk a completely different way of attacking CP violation, and then go to other things like a little bit of leptogenesis and so on. But wait, but not because the angles, but in order to check our measurement, in order to check unitary, you need to measure, because you see, you need to measure sine, not only angle. You put by random, three lines by random. They always form a triangle, or then they are parallel, you know. But then there again is pi, you know, two of them will be 0 and the other one will be pi. That is that if they go forward. So pi is always there. But as you mentioned, yes, the character can be violated because of the sine. Even although you have a triangle, it's not close because, but you have to measure the sine. And then I'll show you how there are tests, mental tests of how the character can be violated.
Yes, about the, can you go to the fifth one?
The previous one is?
Yeah, previous one. It's just about the CKM matrix. There's any reason that you have this symmetry from the non-diagonal parameters? So the VCS, VCD, and VUS, there's nothing one or other, but you can see that's the same parameter. There's some.
You mean here you're referring to this one? It's order of magnitude. It will not be exactly one. It will be.
Yes, but yeah. No. I'm talking about the off-diagonal parameters.
This one here.
It's lambda 2 and lambda 2, lambda 3 and lambda 3. There is a symmetry around the diagonal.
There is no reason. We don't understand that. I will tell you another curiosity about. Now this time is that Khabib was lucky because you see at his time there was no reason to believe that VUS square plus VUD square will be equal to 1. But it's almost equal to 1. So experimentally, Khabib universality at that time, at his time, worked very well. Because VUD measured that time square plus. Even today, if you measure, you can never discover that there is a third generation by just measuring VUD and VUS. You know? Because the knowledge of VUB is so small, you know, the size of VUB is so small that you could not predict, you know. So that is luck that the two generations already saturate unity. In other words, this term square plus this term square, this will be 1 minus lambda squared, this one will be lambda squared, so this is essentially equal to 1. The mistake is lambda to the 6 because it's squared, so it's very, very small. So you could, somehow nature was kind to us. It gave us Khabib universality at a time where the third generation was not done.
Do I need a microphone? Yes, can you hear me?
Yes. Okay. So yes, hello everybody. So first, I would like to thank the organizers, especially Mario and Hugo, for the invitation to be here. It's my first time in Brazil, and as a consequence, also in Rio, in fact. Okay. So my lecture is about massive gravity. And so it's meant to be an introduction to massive gravity. And so it's going to be a Blackboard lecture. So and I will try to follow this roadmap. Can we turn off the projector, maybe? So it's really a lecture for non-experts. So the first lecture is an introduction to this introduction. So it will be hopefully for today. Then I will discuss what is called a Fierz-Pauli theory. Then I will discuss nonlinear completion of this Fierz-Pauli theory. So with an S. And then if I have time, which is not sure, I will talk about other issues. Phenomenology, solutions of the field equations, extensions of this nonlinear completion, and also some open questions. Okay, so the first lecture is meant to introduce or to recall some basic facts about gravity, massless gravity, to start, and introduce some really notation. So it's really not. I don't think there will be much new things there, but it's to set notation for the rest. So. Of some properties of massless gravity, can be called massless gravity. So what I call here massless gravity is obviously general relativity. So meaning general relativity, right? So of course general relativity is a nonlinear theory for metric G mu nu. And which obeys the Einstein equation. So G mu nu of G. So my notation is a big G is a Einstein tensor. So as well known, it's a function of the metric. And then I will allow a cosmological constant lambda, and this is equal to 8 pi G over C4. T mu nu, or whatever. I will rather use maybe units where this is just m Planck minus 2. T mu nu is the energy momentum tensor of matter. So of course this equation have a gauge symmetry, right? Which is general coordinate, general covariance. So if I change coordinate in this way. Tensor transform in a specific way by definition, right? Which is this transformation law. And the same transformation law would hold for the metric. Okay, and this implies, as is well known, Bianchi identity. D mu of G mu nu is identically 0, where this is in my notation, this is a covariant derivative associated to the metric G, right? Okay, and I'm using everywhere Einstein summation convention for indices. I will also use the following convention. So G mu nu equal to eta mu nu will be for a Minkowski metric in a canonical form. That is to say, eta mu nu is just a diagonal of, say, -1, 1, 1, 1. And I will use D to denote the number of dimensions. And I'm using the signature mostly plus here. Okay, and also I will consider Einstein spacetime, which are by definition solution of the vacuum Einstein equation with a cosmological constant. Okay, right. Yes, so I will also use some labels. So, so this equation will be denoted in the following 1, 1, 1. So my convention for the label is that the first numbers without circle are just referring to the section, and the last number is the number of equation of this section. So this is Einstein equation, obviously. One has also, I would like to label this equation referring to gauge invariance. So this equation would be 1, 1, 2. And an Einstein space-time definition would be 1, 1, 3, say. Voilà. Okay. Okay, so this is of course well known. And as is well known as equally, Einstein equations are nonlinear equations, but one can linearize them around some background. So if one does that, if one linearize Einstein equations, so 1, 1, 1 around the background. So around the background G mu nu. So one writes the full metric is just now G bar mu nu is equal to G mu nu plus H mu nu, where H mu nu is supposed to be small perturbations, right? And if I demand in addition that G to be a little bit more general than just linearizing on Minkowski spacetime, I just define G as being a solution of Einstein's vacuum spacetime equation. So G mu nu here is a solution of 1, 1, 3. So that needs to be, I'm linearizing around an Einstein spacetime. Then I get the following equation. Which can be worked out in exercise if you have not done it before. X mu nu is equal to MP minus 2 T mu nu, where X mu nu is an operator that I'm going to write because I will use the form of this operator later. So X mu nu is as the following form. So it has minus 1/2 of d mu h minus 1/2 of box h mu nu plus 1/2 of d rho. So there is several ways to write this term, of course, but here I'm using this way. Minus 1/2 of g mu nu d rho d sigma h rho sigma minus box of h minus lambda h mu nu minus 1/2 of g mu nu h. Okay. So this comes from linearizing the Einstein tensor plus the cosmological constant term. So there is a kinetic operator. Say this can be this is what is in blue here can be considered as a kinetic part. And then there is a cosmological constant depending term, which is this guy here. So it is a cosmological constant term, say. Okay. Yeah, exactly. So thank you. I wanted to add indeed that H is defined as H mu nu, G mu nu. So this is a trace of H mu nu with respect to the background. All the derivative operators are defined with respect to the background here. And box is a trace of the two derivative operators. And in addition, all the indices of H are moved up and down with the background metric, right? Standard stuff. Yeah, if you want to ask question, of course you can interrupt, right? Okay, so this is. Sorry. Thank you. Yeah, this goes fast. Okay, anyway, so these equations are well known to have, well, to lead to different things, of course. First, if you consider the case where now G mu nu, the background metric, is just the flat metric, and then in addition you go to the non-relativistic limit, you recover the Poisson equation, right? You recover, in particular, for the 0,0 component of H, that 0,0 component of H is obeying Poisson equation. Okay, which leads, of course, to the usual potential, right? If I define V as minus C squared over 2 H naught naught, I get that V as the usual form minus GM over R, right? Okay. So now the fact that it is a power law, right? So that's for the case of a localized source, right, of mass M. So I have a power law here, right? And the power law tells us somehow that the gravity is mediated by zero mass particle, right? Is mediated by a massless particle, if one wants to say it in this way, in this little bit Cavalier way. Because, of course, a massive particle would rather mediate Yukawa potential, right? A massive particle would mediate a Yukawa type of potential. So it would give rise to a different potential of the type 1 over r, e to the minus r over lambda c, where lambda c is the Compton wavelength, Compton length. And it is defined in the usual way as h bar over mc, where m is the mass of the particle, right? So to get such an equation, so I need to give a label to this equation here. So this is 1, 4. Okay, and so to get, of course, this Yukawa potential, I just need to solve an equation which is a modified Poisson equation, which is this one, right? V over lambda c square is, say, proportional to some energy density. So this is 1, 1, 4 bis I have some problem in numeration, so I had to add some label at some point. And this is also called sometimes a modified Helmholtz equation. And so this term is also, of course, minus V over lambda C square is also equal to minus, if I use units where h bar and C are 1, this is just minus m square V, right? Okay. Right. So here, indeed, if we now move away a little bit from the non-relativistic limit, we are not surprised to have found in the non-relativistic limit this massless behavior, because this equation do not contain any mass term, right? Okay, so this equation, there is no mass term here. So what a mass term would be in this equation some term of the form m square h mu nu, or possibly m square h g mu nu. And that's all. This is all possible mass terms one can write, which are, so these are terms which are by definition linear into h. So of course there are terms of this type, which are those two terms, right? But those two terms are not mass terms because there is a gauge symmetry of this equation. Because here there is a gauge symmetry, including those two terms, which is that if I change h mu nu to h mu nu plus d mu xi nu plus d nu xi mu, well, this is my symmetry. And I have to include those two terms to get this symmetry, right? Okay. So, the purpose of this talk or this lecture is to discuss, in fact, what kind of mass term somehow you can add to this equation, and what kind of nonlinear completion you can get out of them. Okay. So this gauge symmetry, of course, allows to count also the number of polarization of the graviton. So if I call n0 d, this is the number of polarization of a massless graviton. 0 is for massless. And this is for the number of dimension. Okay, so I can count this easily because I start with an h mu nu which is symmetric. So it has d plus 1 over 2 components. And then I have to subtract the gauge redundancy. So the gauge redundancy are just 2 times the number of parameters of the gauge function. So that is 2d, right? So it gives me in total d minus 3 over 2, right? So I can check that if I am in 4 dimensions, I get 4 times 1 divided by 2. I get that I have 2 polarization. And if I have in 5 dimensions, I would get 5 times 2 divided by 2. So I would get here, I would get 5 polarization for massless graviton. Okay, so this is also a way to check that this graviton obtained from this equation is massless, because from group theory consideration, if I consider the representation of the Poincaré group for a spin 2, I expect that a massive graviton has, in fact, in 4 dimensions, more than 2 polarization, right? A massive graviton, so say group theory, tells me that a massive graviton in d equal 4 should have m4 polarization equal 5 and not 2, right? Yes. Yeah. So in 3, so this, you see, this is 0. It's well known that in if you go to lower dimension, there is no propagating mode, right, for the graviton. Right, so in 1 + 1, and there is no ether propagating graviton, and so this formula has to be a little bit adjusted. Right, exactly, yeah. And so you see in 3 there is 0. It's a well-known fact that if you go to lower dimension, gravity becomes trivial, right? Okay, so that's all for this first little subchapter. Yeah, so let me just again label some of these equations. Sorry. So this should be 1, 1, 6. And this should be, these all things should be 1, 1, 4 labels. 5, sorry. 5. I think I already had a 4 somewhere. Okay. So now let me discuss motivation of this lecture somehow, of why one should be interested into massive gravity at all, right? So why massive gravity? So I think there is a different reason, in fact, to be interested in massive gravity. So I'm going to give maybe 2 of them, but you can add others maybe. So the first reason is that it may be an interesting infrared modification of general relativity. So I put a question mark because this can be questioned. In fact, one can question whether infrared modification of general relativity at all are interesting. But the idea is, of course, the following, can be motivated by the following thing. So we all, of course, believe that general relativity has to be modified in the ultraviolet with a high energy, but maybe it's also, it can also, or it has also to be modified in the infrared. And the motivation there is, of course, coming from cosmology. So in cosmology, we know that from Einstein equation, where I remove the cosmological constant here, so I put it here, we need, usually in cosmology, we need dark energy, of course, and dark matter, right, to feed the data. But those components, so far, are only known via their gravitational effects, right? So a logical possibility is to replace 1 or 2 or both of these components by a modification of general relativity in the infrared, right? Say one could wish to replace this by an infrared modification of general relativity. And since we won the World Cup yesterday, let me just tell you the story of a hero, a French hero, of course, which is not playing football. Who's Le Verrier, right? Le Verrier was famously a very nasty guy, but he was also very clever, of course, because he managed to, as is well known, he managed to predict the existence of Neptune, right? Neptune successfully. So that was in, oh sorry, that's 77. Because Neptune was discovered in 1846, thanks to his prediction, which has at the time a prediction of dark matter, right? You can say, because Neptune was just seen first via Le Verrier calculation, and also one should also mention usually Adams, right? But sorry? Ah, Galileo, sure, but you're Italian, so you're biased. Right, and you didn't win the World Cup. Okay, but not this year. Okay, so anyway, he successfully predicted Neptune, right? Successful dark matter hypothesis. But it also unsuccessfully predicted the existence of another planet, Vulcan, to explain the anomalous motion of Mercury in particular, which he contributed to compute himself. And of course, Vulcan was never discovered, but instead, what was discovered was general relativity, right? So Le Verrier sort of personifies, in fact, the success and the failure of, in fact, both approaches here, right? The dark matter hypothesis and the infrared modification of, when in this case of general relativity, you can maybe argue that it's infrared, but anyway, a modification of of a gravitation theory, which allowed to do something interesting. Okay. Okay, so that's all for my little, say, chauvinistic story. And I should stop because I see some Italian resistance in the room. And let me just give you some numbers. So if one wants to take this idea of infrared modification of general relativity seriously, of course, one should maybe, via an infrared modification, via massive gravity, one should think about what is the Compton wavelength, the appropriate Compton wavelength for such a modification. And so an estimate is, of course, to assume that this Compton wavelength is of the order of the Hubble size, right, today, right? So this Hubble size is about 1.3 10 to the 26 meter, sorry. And that gives a mass, which is, so this is meter, right? And so it gives a mass which is very low, of course, which is of the order of 10 to the minus 33 electron volt, right? So one needs to introduce at hand a very low mass in the game. So one could compare this mass to the bounds on the mass of the graviton we have today. So if you look at, for example, in the particle data group compilation, you find that there is a bound on the graviton, which is the string-Gauss bound is about is not very far from this value for the graviton, even though these bounds are all subject to hypothesis. And but anyway, the fact we need precisely dark energy. For dark matter, it's a little bit different story. The fact that we need those is somehow telling us that we don't know very well gravity at these Hubble distances, right? So there is a nice review on these bounds by Durham, Deskins, Tolley, and Zhu that you can look at if you're interested. On the graviton mass bounds. Okay. So let me say also, I don't know how much time I have. Okay, very good. Yes, so there is also, as you maybe have, discovered yourself reading the paper, the discovery paper of LIGO. If you look, for example, at the LIGO discovery paper, one of these discovery paper, they are able also to put a bound on the mass of the graviton, which is much smaller, much less strong than this one, so it gives a mass which is 1.2 10 to the minus 22 electron volt. Okay. Yeah, it's a good question. Yeah, I don't have an answer to this question, and I don't want to push this idea too much because now I'm going to give you another reason to be interested in massive gravity. And so, in fact, that's also, I'm not sure if I will have time to discuss really application of massive gravity to this idea of cosmology, etc. But I think whatever you think about this modification motivated by cosmology, I think they are interested fundamentally just for the purpose of understanding what could be a massive gravity theory. And this will last for sure, even if we don't discover any infrared modification of gravity. Okay, so another reason maybe for being interested in massive gravity is somehow extra dimensions. Because we know that if we consider extra dimensions, we have automatically, or we can interpret things with massive graviton. Okay. So So here I'm going to remind some basic facts about Kaluza-Klein mechanism. So first, if we consider a phi scalar field, living, say, in 5D, in 5 dimension. Okay, so this scalar field obeys, say, it's in vacuum, so it obeys some vacuum Klein-Gordon equation, right, of this type. Where this is four dimension, and this is the fifth dimension. And this is equal to 0 if I don't have a source, right? Okay, so now I can do something which is I can Fourier transform the field along the fifth dimension, phi along omega, which parameterizes the fifth dimension, right? And let's assume for simplicity that this fifth dimension is compact, right? Just to allow me to have a sum instead of a continuous Fourier transform. But then I can decompose my field as a Fourier transformation, right? A Fourier component. Of this type, where R is a radius of this curly dimension, right? And this is omega. Okay, so then if I insert, of course, this decomposition in the Klein-Gordon equation, I get, so inserting this in the Klein-Gordon equation, in the equation here, right? I get that the Fourier mode verify the following equation, right? Okay, where I recognize now this operator, which is just the usual D'Alembertian of phi k. And then I have a term which I can interpret as a mass term for phi k if I define mk square as k square over r square, right? So it means I can interpret, first I can give a label to this equation. I can call this 1, 2, 2, 3. Maybe I missed some labels previously, but I don't think this matters so much. No, this is okay, I guess. No, I guess I missed some. Well, okay, this doesn't matter so much. Okay, anyway, so this is now a massive Klein-Gordon equation, and this is a standard statement that a massless field in 5 dimensions can be decomposed into a sum of Kaluza-Klein mode, right, of massive mode. Each phi k is a massive mode, except that if k is 0, right? Okay, so this can also be done from for the graviton, right? If I do this, the same decomposition for the graviton. So let's do it briefly. It works as well for the graviton. And so a similar result holds for the graviton. Okay. So here I can do it in a slightly different way. So I could have also done this decomposition for the scalar at the level of the action. So let's do it for the action of gravity. So I start with a 5D Einstein-Hilbert action. Okay, which I didn't recall, but I guess you already know that it gives back the Einstein equation, right? So without cosmological constant here, and I decompose my 5D metric a la ADM That is to say, I'm doing a 4+1 split, or 4+1 split of the metric, except that the one here is now supposed to be the omega dimension, so it's space-like. Okay, so if I do such a split, I can introduce here. I have a 4-dimensional metric, so this is 4 by 4. This is here 1, so I have some n mu vector, and here I have a curly n square plus g mu nu n mu n nu. Okay, and this is symmetric. So if I decompose now the Einstein-Hilbert action this way, I get that this action is now m5 cube integral of d4x dy or d omega square root of minus g. Then I have this curly n here in factor of everything, r plus here k mu nu k alpha beta times g mu nu g alpha beta minus g mu alpha g nu beta. Okay, and k is some can be called extrinsic curvature of the omega equal constant surfaces, but it has this form which matters for us. So it is the only place where derivative with respect to the dimension, to the coordinate y, which parameterizes the 5th dimension, appear, right? So this is this prime here. Primes means d omega, right? Okay, so now if I do the Kaluza-Klein trick, somehow if I Fourier transform along the extra, yes, sorry? So here I just rewrite this action using this decomposition. Ah, yeah, sorry, yes, yeah, absolutely, yes, this is 5D metric, sorry, yes. Sorry, and here this is the 4D metric, yeah. Thank you, yes. So, yeah, exactly. So, okay, so if I do the Kaluza-Klein stuff trick, right, if I Fourier transform everything along the omega direction, because in this decomposition, the only place where omega derivative appear are in this term, I get, out of this term, I would get a specific form here for the Kaluza-Klein modes. I would get some m square k, say, in a similar way as over there, times the Fourier mode of the graviton. And say I do this decomposition where I suppose this metric is flat, right? Then I would get okay, something which is proportional to this tensor here. Okay, so not only do I get massive gravitons, which are the Kaluza-Klein modes of the graviton, but I get a specific mass term as well, right? I said at the beginning that one can add 2 mass terms a priori to the initial Einstein equation linearized, but here you see I get a specific form, which is this one, m square h square minus h mu nu h mu nu. Okay. Okay, so this is the celebrated Fierz-Pauli. Ah, yeah, now I understand this 3 because I put a 3 because now there is a 1. Okay. So anyway, so this is a celebrated Fierz-Pauli mass term that I'm going to discuss later, right? So this is Fierz-Pauli. So it's only one possible mass term, but it is a good one that we get by this decomposition. Okay. So we also can learn something else from this discussion, is that we can learn how to count degrees of freedom for a massive graviton with this mass term, because we have learned that if I consider a massless graviton a massless graviton in d+1 dimension. Because I can do this decomposition here for this massless graviton, I should have the same number of degrees of freedom than for a massive graviton, but in one less dimension, right? So, so this is the number of polarization of a massive graviton in d dimension, and it should be the same as the number of polarization of a massless in d+1. And so we just need to replace now in the formula I gave previously the d by d+1, right? And we get that it is d+1, d+2, d-2, sorry, over 3, which I can also write as d+1, d/2, sorry, over 2 minus d+1, right? Okay, so this is now this is counting the number of components of a symmetric tensor, and here is counting the number. You see, you have d condition. So this would be taking into account the transversality of the graviton, and this would be for the traceless property, tracelessness. Okay. So you see, you can see also it works that with the previous counting. So this will give me, my equation 1, 2, 2, 2. Okay. Right. So usually, of course, you do this decomposition in Kaluza-Klein mode when this was introduced by Klein for a compact extra dimension, but you can do it also for a non-compact extra dimension, in which case, instead of having some Fourier sum, you have a Fourier integral, right? Okay, so that's all for this maybe two motivation for being interested in massive gravity. Yeah, let me stress also that if you do this Kaluza-Klein decomposition of general relativity, of course you get some theory which has a quadratic piece, right? But you get also, because general relativity is nonlinear, you will get a mixing of all modes, right? If you go to cubic, etc. And this is a crucial aspect of this, because the question is whether you can write a theory for just a single massive graviton, while here you have an infinite tower of massive graviton which interact together in a specific way in order to recover the initial theory, right? Okay, so is there a question so far? No? Okay, so let me now turn to another point, which is there somehow for historical reason, but also because it gives an example of a theory with extra dimension, which has this massive graviton there. And this is a DGP model, the so-called DGP model. And this model is sort of an invitation au voyage, as we say in French, but so it's an invitation to take the trip if you want. And so this model was introduced now almost 20 years ago by DGP, which states for Dvali, Gabadadze, and Porati, who were most of them were at New York University at the time, except maybe Gregory Gabadadze, who was a postdoc in Minneapolis. But anyway, this model is interesting because it provides an example of some theory which features some property of massive gravity with extra dimensions, but also because it's basically the reason probably why I'm giving this lecture today, because it's really started a renewal of interest into massive gravity theories, which were considered before, but which were largely forgotten or discarded for good reasons, in fact. So I want to introduce this model here, briefly. So this model is a brain world model. which can be introduced in the simplest setting by saying you consider a brane, which is a 4D hypersurface in a 5D dimensional space-time. So let's consider a coordinate x mu on this hypersurface and say xa on the whole space-time, and it has the following action. So it has the usual action for gravity in 5 dimensions. So yeah, okay. Let me put a 5 here now, or maybe I will put a tilde to say this is a 5D metric. So I have a tilde metric. Okay, then I have some brane localized matter, which I imagine to be the standard model matter. Say, and this G without tilde is just the metric on the brane, right? Which is which also called the induced metric. And so this is the standard brane world setting for brane, a 3 brane. 3 brane is 4-dimensional surface in a higher dimensional, in a 5D bulk. But then I add, and this is specific to DGP, I add a brane localized Einstein-Hilbert term, right? And this term here is really somehow proper to DGP. Okay. So it was not considered before somehow, or at least its effects were not really considered before GGP. And so it changes a lot of the usual brane world story, which you can see in various ways. But one way is to consider a scalar toy model first of this type of construction. So let's consider a scalar toy model for that, for DGP. So to do that, you just do the same construction as for DGP. So you consider an action S, which is now, say, a 5D action for, let me call Y the extra dimension, now for a scalar. And then you consider some localized term on a brane for this very same scalar. So the equation of motion for this theory are the following, right? So you have a 5D Laplacian, say, on phi, plus some 4D Laplacian multiplied by some delta function. And this is equal now to some, say, localized source, right? So you can easily compute the green function of this equation, as was done by DGP. And moreover, you can write the associated potential, right, between due to an exchange of this phi, right? So you find the following using a Kellen-Lehmann representation. You find that the potential, if you consider 2 sources on the brane, the potential of interaction between these 2 sources is proportional to 1 over m5 cube, and there is an integral over the Kaluza-Klein mode e to the minus mr over r. So here I assume in addition that the 5th dimension, so the one parameterized by coordinate y here, okay, is just infinite and flat. So I assume infinite and flat bulk. So just the bulk is just a slice of Minkowski which you slice with, where you put on the hypersurface, and that's how DGP model is defined. So you can question, of course, the physical reality of this model, but it is interesting as a third model at least, and it gives this as a Kaluza-Klein decomposition of the potential. So you have a Yukawa suppression. This is for each Kaluza-Klein mode, and then you have this prefactor where RC is a distance scale, which is mp square over 2 m5 cube. At least that's the RC you find for the graviton. If you would do the same calculation for the graviton, you find this. And so as a result, it's easy. I don't know how much time do I have.
5 minutes.
Ah, yeah. So as an exercise, you can easily find out that this form factor gives rise to two different behaviors. So you find that V of R behave like 1 over R, that is to say as in 4 dimensions, for R smaller, much smaller than RC. And it behaves as 1 over R square for R much bigger than RC. So it's easy to get this behavior from this form here. And so you have a model where gravity, because the same would be true for the gravitational potential, gravity behaves as in 4 dimensions for small distances, and as in 5 dimensions, that's in 5D, sorry, that will behave as a 5-dimensional potential for large distances. And in addition, you see that if you do the same for gravity, you discover you have the same type of decomposition here, and in fact, you discover that
On the brain.
Yeah, on the brain, yes. Gravity. That's for 2 localized sources on the brain. And so, if you do the same calculation for gravity, you have the same type of Kellen-Lehmann decomposition here, which tells you that you see gravity is mediated by some resonance of massive graviton. So it's a continuous sum of massive graviton. You don't have zero mass graviton, which is isolated in this spectrum. And so it's some kind of massive gravity, which is complicated, but which gives this behavior. And in fact, the cosmology of this model has been worked out. And if you work out this cosmology, you find the following equation. You find that the Hubble law, the Hubble equation, Friedmann equation, the usual one is replaced by this following form. So you have this form here. Okay. So here you have, so this is what replaces the second Friedmann equation. And so here you have 2 different branches of solution. The raw matter is the energy density of matter. And you see what's going on if you choose, for example, the plus branch of solution. When rho, the energy density of matter, is decreasing, you get to the following equation. You get that h squared plus k over s squared. So a is the scale factor of the universe on the brain, and h is the usual Hubble factor. It's just 1 over RC square. Right? And so you have a solution which is usually called self-accelerated solution, which is a solution which, it's the same equation you would get from a cosmological constant in a Friedmann equation. And so without here having introduced any cosmological constant. Okay? So while if you are, and so this was one of the interests of this model, even though it was not introduced for that purpose, but it was discovered that this is behavior, that you get, you can replace somehow dark energy here by a large distance modification of gravity. While, so this happens at late time. This happens when, say, h minus 1 is much larger larger than RC, this critical distance scale, while in the early universe, and I will end here because I see that Hugo is standing up. In the early universe, that is to say when H-1 is much smaller than RC, then this term dominates and you recover standard cosmology. Cover 4D cosmology. Okay, so that's I think I will stop here for today, and that was another motivation if you want to be interested in massive gravity, and I will discuss in the following lectures some of the properties of this DGP model, even though this will be some kind of side story, because the main story will be about really massive gravity for a single massive graviton. Here you have an infinite tower of massive graviton, which is a much more complicated setting. Thank you for your attention.
Sorry, I'm a bit confused.
Sorry?
I'm a bit confused. Perhaps
Okay.
you could clarify.
Sorry.
I got the impression that we don't have one massive gravity. Is that right?
Yeah, so as I said, in this model, we have an infinite tower of massive graviton, right? In fact, we have a continuum of massive graviton.
You've got possibilities.
But I will discuss after. So in the rest of my lecture, I will mostly discuss theories with one massive graviton. Just one.
Another question is related to the speed of the gravitational waves.
Yeah.
Would you expect to have C or
so
very close to C in this context?
I will talk about that later. Yes, but indeed, yes, this is a good question. Yes.
I have a very general question. As you showed, you are modifying the what we'll say. I mean this Coulombian potential.
Right.
Okay. So in standard gravity, the mass term in the Coulomb potential has a very deep meaning because it can be shown that is basically the ADM mass.
Right. Yeah.
The ADM mass, it is possible. I mean, you can really show it is associated to a current, which must be conserved.
Yes.
So now the question is, in your case, what is the ADM mass? How is
so
that? Can
I
you
will
define that, something like that?
I will address this in the following lectures. You know, the bottom line is that in this massive gravity theory, you either break explicitly the Diffeo invariance by introducing some background metric, some pre-geometry, as it is sometimes called, or you keep two metrics, right? Two being dynamical, sorry, and then you still have gauge invariance, but you have now more degrees of freedom in the gravitational sector because you have one massless graviton and one massive graviton. And but I will also address this question when I will be discussing what is called the Weinstein mechanism, which is a way to recover usual solutions of general relativity in a nonlinear massive gravity theory.
I don't know if I got this right, but you completely lose the interpretation of geometry. I mean,
well, in what I said, not completely, because first of all, I have not introduced yet, the theory of a single massive graviton, right? I just introduced some motivation, if you want. And so if I just stick to the theory, now I introduce with several massive gravitons, which is DGP model, right? You have a geometrical interpretation of everything, right? Because the you have a surface, right, which is embedded into higher dimensional bulk, etc., with one induced metric on this surface. So there is no clash with usual geometric interpretation of just having one single metric in our universe. Say just that our universe is just a surface now living in a higher dimensional bulk space-time with also geometry. But you're right, now if you consider the case of a single massive graviton, which I will introduce later, you sort of, you have a different setting in the sense that you need, if you just want to have a single graviton, you need another metric in the universe. So you need what is called a pre-geometry sometimes, so you need to have two metrics in the game. And so then you can question the geometry maybe also. Associated with these two metrics, there is interesting issues of how you can put two metrics on the same manifold, right?
Any other question? Not? Thanks. We will convene tomorrow at 9 sharp. We start the second day.